Okay, so now we're towards the end of Newton's second law. We need to think about applying Newton's second law to uniform circular motion, or circular motion that's not necessarily uniform. But remember what uniform circular motion is. It means that you're going in a circle. That's a terrible circle. Pretend it's a circle. It's a potato with a radius r. And, and if, let's say, you're a car going around a track, or you're a ball on a string, whatever you are, you can be whatever you want to be. Let's say, so you're traveling in the forward direction, so your velocity is always tangential to the circle. The radius vector points from the center of the circle to where you are, and the acceleration at any instant is the centripetal acceleration, which is v squared, the speed squared, divided by r, by the magnitude of the radius. So this is the magnitude of the acceleration, and the direction of the acceleration is, the direction of the centripetal acceleration is always towards the center of the circle. So that's just a reminder of where we were with uniform circular motion. Now I will say here, what if it's not uniform? If it's just circular motion, that means that instead of going at we didn't say. Uniform means constant speed, that you're going at constant speed around a turn in a circle, whatever. But if it's not uniform, it means your speed is changing. If it's not uniform, it means speed is changing, so you're speeding up or slowing down as you go around this circle. And what that does is it adds a tangential component to the acceleration. There's still a centripetal component, and the centripetal component, whether your speed is changing or not, at any instant is always v squared over r. But if your speed is changing, you also get a tangential component of the acceleration. The net acceleration is a sub c plus a sub t, right? Those are the two components. So the net acceleration of the two components drawn, right, we could add them together, put them head to tail. So there's a net acceleration, which is no longer towards the center, right, the total acceleration. And by the way, what would, for example, this acceleration imply about this velocity? It would imply that the speed is slowing down, right? The acceleration is in the opposite direction of this velocity, so the speed is slowing down. In any case, so you can have a tangential acceleration and a radial acceleration, the radial one being the centripetal one, the one along a radius. But most of the time we'll just stick with uniform circular motion, so we don't have to worry about the tangential. But just understand that we can add in a tangential component. It doesn't change anything about the fact that there's still a centripetal component, which has an acceleration v squared over r. And the fact that we can measure, like for uniform circular motion, we know that the acceleration towards the center of a circle is v squared over r, means that we can still do Newton's second law problems. What do I mean by that? Let's say that I have a ball on a string. This is a ball on a string. I'm trying to think of what else it could be. And I'm rotating that. Look at that perfect circle I drew. That was actually the circle function. And I'm rotating it at a constant speed. Let's say that the speed of that ball wish I could draw a straight line. V is equal to 3 meters per second. And let's say that the radius of the circle, let's say I have a string which is 0.5 meters. The string is 0.5 meters. What is the tension in the string? Let's just assume that the only force is the tension in the string. Just ignore gravity, ignore air resistance. We always ignore air resistance unless you're otherwise told. But let's ignore gravity, even though it's kind of hard to do. Actually, the way we would do this to ignore gravity, which would be perfectly valid, would be a vertical circle instead of a horizontal circle instead of a vertical circle. So, for instance, this could be the ball could be sitting on a desktop, and we could pin down the string, and we could just start rotating the ball around that pinned down string. And there would be a normal force perpendicular and gravitational force perpendicular, but those would not participate in the rotational motion. But in any case, we're just going to pretend that there are no other forces other than the tension in the string. So, what is the tension? Well, so let's go ahead and draw a free body diagram of the ball. Let's take the ball and just going to take it out of the picture and draw a free body diagram. if the only force is the tension in the string, then we've got F sub t towards the center of the circle. And that's it. That's the only force. We just said it was the only force. So now we choose our axes. Now what's the direction of the acceleration, right? Sorry. How did I know that the only force was towards the center of the circle? Because this string is under tension. And so the string is pulling the ball towards the center of the circle, because what does the ball want to do? The ball wants to move in this direction, but it keeps on pulling it back towards the center of the circle, keeping it from moving in that tangential direction. So the tension, it's just the fact that the string is under tension that you know that the tension is always along the string. Wherever a string is attached to something, it pulls away at that point with the tension in the string. So this is a correct free body diagram. And so then we draw our axes. Well, what's the direction of acceleration? We know that the direction of acceleration is towards the center of the circle. So I'm going to choose that as the plus x direction. Oops, that was just meant to be part of the axis. Okay, so that's the plus x direction because the direction of the acceleration is towards the center of the circle. And the y, we don't need a y direction. This is one-dimensional. And so then we can apply Newton's second law, F net equals ma. It's one-dimensional, so that's all along the x direction, or we could just say F net x equals max. The net force in the x direction is F sub t, and F sub t is equal to the mass of the ball times the acceleration. The acceleration, because it's going in a circle, we know that the acceleration is v squared over r, because it's going in a circle. So what have we done? We've done a Newton's second law problem. We drew a picture, we drew a free body diagram, we wrote down our axes, we chose our axes, we wrote down Newton's second law, and then we filled in the force, the left-hand side from the free body diagram. We filled in the acceleration on the right-hand side from anything we know about the acceleration. In this case, because it's going in a circle, the acceleration must be v squared over r. And so therefore, the tension is mv squared over r. I didn't give you mass of the ball. I got to give you a mass. I do have to give you a mass in order to solve this problem. Let's say that the mass of the ball is 50 grams. No, 50, we already used 5. Let's say the mass of the ball is 40 grams. 40 grams. Okay. So now it's just a plug-in. So the tension in the string is 0.72 newtons. That easy, right? So it's just a Newton's second law problem where we know the acceleration is v squared over r. So that's the only real addition to Newton's second law in uniform circular motion. Let's see what else we can do with this. Let's imagine the space station is in orbit around the Earth. That's a roundish Earth. So I just drew a satellite, space station, whatever. Let's say that it's in orbit. It's a low Earth orbit. So it's about they're about 100 miles above the surface of the Earth. So the radius is the radius of Earth plus 100 miles. Okay. So first of all, that's the radius. And let me ask, how fast is it going and how long does it take for it to do an orbit of the Earth? Okay. So this is, whoops, I meant to draw a different color. So it's orbiting the Earth, and I want to know how fast it's going and how and what the period of orbit is, how long it takes to go around the Earth. First of all, remember why a satellite orbits Earth. Why does a satellite orbit Earth? Or why does the Earth orbit the Sun? Or why does the Moon go around the Earth? Why does anything orbit anything else? Because the gravitational force is pulling it towards the surface. But because the surface is not flat, because it's round, if you give the object a large enough tangential velocity, as it falls, right, the acceleration is towards the center of the Earth. That's supposed to be towards the center of the Earth. It always misses because the thing it's orbiting is round, it's not flat. And that's what an orbit is. We've gone over that before. So the whole reason why the force that's keeping the satellite in orbit is the gravitational force. That's what's keeping it, that's what's making it accelerate towards the center. That's what's making it go in the circle. Okay, so in a low Earth orbit, the force of gravity is really similar to that at the surface on Earth. So we're going to assume that, and I'm going to ask what is the speed and period of the orbit. Well, let's draw a free body diagram of the satellite, and I'm going to draw it in the position where it is, right? So that means that the gravitational force is pointing in that direction. That's the gravitational force, Fg. And that's it. That's the only force on it, right? There's no strings attached. There's no friction in outer space. That is truly the only force on an object in orbit. Okay, so let's choose our axes. Again, it's a one-dimensional motion problem. It's accelerating towards the center of Earth, so I'm going to call that plus x direction. Again, hopefully you understand. Just move this over here, and right, we're getting that the gravitational force is in that direction, and the acceleration is in that direction. Okay, let me undo some of that. All right, so then we apply Newton's second law. F net x equals ma x. The net force in the x direction from the free body diagram is F sub g. And the mass of the satellite, and no, I did not give you the mass of the satellite or the space station. We can always look it up if we need it. And the acceleration is going in a circle. So this is where, because it's circular motion, I can always plug in v squared over r for the acceleration. Okay, so therefore, Fg, which is just the weight of the satellite or the weight of the space station, even if it's heavy, it's still mg. Remember, because the force of gravity is similar to that on the surface of the Earth, the weight is still just mg. Now, let's say that we knew that the force of gravity was 10% less, then g would be, instead of 9.8, it would be 10% less than 9.8, 10% of 9.8, 9.7, right? But anyway, we're just saying it's similar. Okay. Mg is equal to mv squared over r. The m's cancel. Look, we don't need to know the mass of the satellite. In other words, it doesn't matter what the mass of the satellite is. All satellites at a fixed radius go the same speed. Doesn't matter if it's a little tiny satellite. You know that Elon Musk is putting up these little tiny satellites, like I think they're like mug-sized. These little tiny satellites, and he's putting up thousands of them. Did you know this? It's really kind of interesting, cool, a little bit scary. Scary in the sense that now there's a whole bunch of detritus out there that wasn't out there before. But all these little tiny satellites, he's putting them in orbit. But they'll go the same speed as the space station. If they're at the same radius as the space station, they'll all go the same speed, independent of mass. Because you can see here, therefore, that the speed of the satellite at radius r, and it doesn't matter what the radius r is, as long as the acceleration due to gravity is still g, the speed of that satellite is the square, well, I mean, as long as the acceleration due to gravity is g, whatever g is at that point, the speed of the satellite is the square root of rg. Just solve this equation. Speed of the satellite is square root of rg. So what is the radius of the Earth?
Earth's radius is 3,959 miles.
Okay, so you see that Alexa is good for something. 3,959 miles. And so that means the radius of the low Earth orbit satellites, or the space station, which is about 100, I think it's 120 miles up, but let's just say about 100 miles up. We could always look it up if we wanted. This radius is therefore 3,159, well, 4,059 miles, which we need to turn into meters. Squishing it into the corner down here, but convert 4,059 miles to 6.53 times 10 to the 6 meters, multiply it by g 9.8, take the square root, and the speed of the satellite is, that gives me exactly 8,000 meters per second. So that's how fast the space station is moving. That's how fast a low Earth satellite moves, 8,000 meters per second. That's 16,000 miles an hour. That's pretty darn fast. If it's going slower than that, what does it do? If it's going slower than that, what does it do? It doesn't go fast enough to miss the Earth, and it eventually hits the Earth, right? So if it's going faster than that, it escapes, but that's the speed that it needs to go in order to orbit at the radius that we gave it. Okay, 8,000 meters per second. So what is the period of the orbit? Aha! Remember that speed is distance over time. If you're going at constant speed, which we are assuming here, constant speed, so we could say it's the total distance around in one orbit, 2 pi r, divided by the period, the time for one orbit. So this is typical for something moving in uniform circular motion. The speed is 2 pi r over t. That's distance over time. That's just distance over time for a constant velocity. So it is, just solve for the period. T equals 2 pi r over v. Plug in r and v, which are given at the top of the page, and we get the period is 5,128 seconds, which is about 85 minutes. The space station orbits the Earth once every 85 minutes. Go ahead and look up the period, see if we're close to right. Hey Alexa, how long does it take the space station to orbit the Earth?
Here's something I found on reference.com. The International Space Station takes 91.63 minutes to orbit Earth.
Okay, so Alexa says 91 minutes, so we were pretty close. Pretty good estimation. Okay, here's another quick one. A car goes around a circular track, radius 200 meters, at top speed of 40 meters per second. That's around 80 miles an hour. So V is 40 meters per second. Top speed before it slips. It'll slip if it goes any faster. What coefficient of friction is required between the tires and track? What's the minimum coefficient of friction required? All right, so how do we do it? Same way we did the others. Draw a free body diagram. Sorry, I was about to do something. What are the forces on the car? What are the forces on the car? Things I should have said is a flat circular track. We don't want to bank it to make it complicated, so we have to take components of vectors, so it's a flat circular track. Let's just think about the car. What is the force that's holding the car on the track? In other words, keeping it from going straight out this way. What force is holding the car on the track? Hopefully you can see that if I do a top view of this car, if I just take the car and draw a free body diagram just like that there is a force pushing it towards the center. That's what's allowing it to go in the circle. That is a frictional force, right? It's friction. If there was no friction, the car would go straight. You have to have friction to go around a turn. And the friction points towards the center of the turn. So there is a frictional force. Are there any other forces on the car? It's going at top speed 40 meters per second, so it's constant speed. It's going at a constant speed. I'll just say that, but you should imply that. And are there any other forces? You say, well, of course there are. There's gravity and normal. All right, so let's look at it. So this was a top view, right? That's a top view. What about a back view? Like, let's look at the back of the car. Your eye is here, right? So your eye is here. You're looking at the back of the car. So this is a back view. So it's going into the page. The frictional forces in that direction is still towards the center. And what other forces are on the car? Well, we know it's on Earth, so there's a gravitational force. And we know it's on a surface, so the surface must be pushing up. It's a normal force. Go through your list of forces. That is it. Okay, so now let's do a Newton's second law problem. Okay, what's the direction of acceleration? Well, it's accelerating towards the center of the circle. It's accelerating in this direction. So let's call that the plus x direction because that's the direction of acceleration. It's not accelerating forward. It's not accelerating up. It's accelerating towards the center of the circle because it's traveling at constant speed. And then now we have two dimensions, so we can just call this the y direction. Up or down, I don't care, y direction. Okay, so let's apply Newton's second law. F net x equals max. F net y equals may. And then look at this free body diagram. First, we'll address the forces in the x direction. In the x direction, all you've got is ff plus ff. And that's it. Equals max. What about the forces in the y direction? In the y direction, we've got Fn going up, we've got Fg going down, equals May. So as always, we plug in the forces into Newton's second law from the free body diagram. That's what we've done here. Okay. Then we evaluate the right-hand side. We know that the acceleration in the x direction is v squared over r because it's centripetal, it's going in a circle. Centripetal acceleration. In the y direction, what's the acceleration in the y direction? Shout it out. It is 0. It's not moving up or down. So therefore, right, I want to point out that we do have a y direction here, which we didn't in the last two problems, but in the x direction, it's exactly the same equation every time. It was a single force, which is keeping in a circle, is equal to mv squared over r, right? It's a single force that's keeping it in a circle that's equal to mv squared over r. It's a single force that's keeping it moving in a circle that's equal to mv squared over r. In this case, it was a tension. In this case, it was gravity. In this case, it's friction. You've just got to figure out what the force is that's keeping you in the circle. And that force is called the centripetal force. Right? The centripetal force is the force that's keeping you in the circle. It's not an additional force in our list of forces. It's just the name of the force that's keeping you in a circle. So we'll come back to this. Let me just define centripetal force. To summarize this thing that we just realized is that the net inward force is always mv squared over r, right? In this case, we've always chosen the x direction to be the inward direction. And the net force in the inward direction is always mv squared over r. That is what's called the centripetal force. The centripetal force is mv squared over r. It's the net inward force. It's not an additional force on the free body diagram. It's the net force from the free body diagram. Okay, let's come back to this problem. Okay, so we've got ff equals mv squared over r. And we can take that, we can write that ff. But the additional question here is, what kind of friction is this? Is this kinetic or is it static? That's an interesting question. Be very careful here. Again, a little bit of an aside to think about. When a car's wheels are rolling on a road, they're not slipping. The center of mass of the car may be moving, but they're not slipping, they're gripping. Right? Think about a tire on a road. It's gripping the road, and that's why the wheel is moving forwards. What would happen if it was slipping? If the wheel was slipping, the car wouldn't be moving forwards. So what kind of friction is this? This is static friction. You might say, but the car's moving, but the car's not slipping. So it's static friction. If you look at any point on the tire and the road, the tire is not moving. The tire, where it's in contact with the road, is not moving relative to the road. So this is actually static friction. So it's FFS. And, okay, so we got to understand it's the static frictional force that's making the car stick to the road. That's keeping it from slipping. Otherwise, it would be kinetic. And we said it's moving at its maximum speed without slipping. So this is FFS max, because we said it's moving at maximum speed without slipping. So therefore, we can go ahead and substitute mu sub s Fn is equal to mv squared over r. And I asked the question, what is the coefficient of friction? Well, first of all, it's a static coefficient, but we can go ahead and solve for the coefficient of friction. Therefore, mu sub s, whoops, let me draw that nicer. Mu sub s is equal to mv squared over r divided by Fn. But what's Fn? Well, look, we have a second equation. We have the y equation. In the y direction, we have Fn minus Fg equals 0. Seen that a lot before. Right? In the y direction, we've got Fn minus Fg is equal to 0. Therefore, Fn is equal to Fg, which equals mg. So therefore, mu sub s is equal to mv squared over r divided by mg, which is v squared over rg. So that is the coefficient of static friction required to keep the car on the road, and we can go ahead and plug in 40 meters per second was the speed that was given. The radius is 200 meters, and g is 9.8 meters per second squared. Plug that into the calculator, and that gives us a coefficient of static friction of 0.82. Seems quite reasonable for race car tires on a road. You want them to be quite sticky. Seems quite reasonable. But what I really wanted to show here was that these three very different problems, race car on a track, satellite in orbit, ball on a string, are really all done in exactly the same way. There was a single force that was keeping it in a circle. So now let's get a little bit more complicated, and let's look at problems where we have more than one force contributing to this centripetal force. The net inward force is more than one force.